Let's proceed to next example. If you can refer to your textbooks, page 340, problem 7.18, part B. This case here, we are given a hollow conducting cylinder which has inner radius of A and also has the outer radius of B, and the conducting cylinder carries a current along the positive Z direction. So if I draw in 2D view on the XY plane, I will just look the current like a dot, is it? Because the current is coming out, so it's just a dot because current now flowing in positive Z directions. So the question asks us to find the hash everywhere. It means that we have to do same process to find the hash field in any regions. So if you see from the diagram, we have three different regions. The first one within these regions, which is the R less than A, and then the other one here, second over here, which is the R less than A, more than A less than B, and then the last region is over here, the outer cylinder structure, which is for the case of R more than B. So since this is a case of symmetrical structure, and also we assume that this is very long conducting cylinder, so we can simply use the ACL to find the hash field. Alright, let's look at the first region, which is region for the case less than A, the first regions. So again, to apply this ACL, which is closed integrations, the H dot dl equal to the I enclosed, right? Okay, let's point, or let's decide anywhere, any point within this region. Let's say I choose at this particular point, becoming our point of interest. So again, if to apply this ACL, we need to draw our Amperian loop that must pass through the point and also must be closed. So let's say this is my Amperian loop. It must be closed and pass through the point of interest, or let's say at certain R distance. Alright, if you see from this Amperian loop, is there any current that enclosed within this loop? No. For this case, we don't have any current enclosed because the current only exists from A to B. It means that everywhere with less than A, there will be no current. So from these equations, we can simply put here the H dot dl equal to 0, right? Because no current enclosed within this Amperian loop. Alright, so in short, we can simply say that the H for this region actually 0. Okay, now let's look at to the second regions. The second region actually we focus the area more than A and less than B, which is these regions. So again, let's decide any point within the region. Let's say I want to choose at this particular point. So I want to use this ACL, so I need to draw the Amperian loop that again must pass through the point and must be closed. So let's draw, let's say this is my Amperian loop. Okay, let's say this point have distance from origin at this R. Okay, so that's our point of interest, and this is our Amperian loop for the second regions. So again, let's apply the ACL, close integrations, the H dot dl equal to the I enclosed. Alright guys, so the I here, we can actually find the total I by finding the current density. So since the current here appear from R equal to A until R equal to B, so actually the current now plays with the area, right? So we can have the density in terms of density value. It means that we can have a volume current density, right? Because this current now appear from R equal to A until R equal to B. So basically we are going to have volume current density. So let's find the first step to find the J, which is our volume current density. The J has unit of ampere per meter squared, right? Because deal with area. So again, for this case, we have a total I given as here. I, just put I over there. And then just put the area, I mean the effective area for the structure, which is from R to A until R to B. So find the effective area excluding the hollow area in the middle. So now we're going to have pi B squared minus A squared. That's going to be your effective area for this current. So that's going to be our volume current density. And we know that this volume current flowing in positive z direction. So you can simply put direction over here, positive z, with unit of ampere per meter. So that's our volume current density. Alright, to find the I enclosed, if you see from this diagram, for the second region, the I enclosed only appear at R equal to A, right, until R equal to R, right? So we just integrate the I here, integrate the JS, no, the J only, dot ds. Okay, so now we can have the J obtained earlier. So now just take the S, the ds that involved, which is this particular area only. Alright, from where? From R equal to A until R equal to R. So be careful on the limit, right? So now let's proceed. Again, for the DL, for this case, same, they are in circular path. So you just simply have the H become 2 pi R. That's normal, same as previous. So now to find the current enclosed. Again, I would like to remind you the current now only exists between R equal to A until R equal to R. More than R, there's no current will be considered, right? So now just put the integration to the J given previously, I Z component pi B squared A squared, a dot. Again, if you take a sample, that's my sample of area. So again, the sample, guys, will have again same in positive z directions, r dr dphi. So just put here again z directions, r dr dphi, right? So let's proceed the integration process. Again, z dot z will have 1, so take out all this constant outside the integral path. You have here I pi b squared minus a squared, and then integrations for the r again, r dr. Again, the r here, guys, involve only refers to the current that enclosed, which is from r equal to a until r equal to r. So make sure you be careful with that. So now from a to r, right? And again for the phi, just d phi, since it's circular in full, so 0 to 2 pi. So if you solve, you'll see I I'm gonna have here pi b squared minus a squared. For this case, gonna have the r squared minus a squared over 2. Then this part gonna have 2 pi. So let's simplify the equation. 2 with 2, pi with pi. So you can have finally your equation become for the h. I have here the I r squared minus a squared over 2 pi r b squared minus a squared. And we know that, guys, the h for this case actually will be in phi direction, so you can simply put the phi component and ampere per meter. Alright, so that's the value of the H that appear within the second regions, which from R equal to A until R equal to B. Okay, so that's a general equation. So if you want to find the H at any particular point, let's say you want to find the H at R equal to 3, the 3 within this A and B, so just put the R become 3 and the rest value. Okay, so now proceed to the last region. The third region here actually refers to the region which is R more than B. So again, using the same integral formula or SEL, the H dot dl equal to the I enclosed. Alright, let's say I want to choose any point outside the cylinder structure. So let's say this is my point of interest. So again, let's draw the Amperian loop, which must pass through the point of interest and also must be closed. So that's the condition must be met first. Okay, let's see your Amperian loop. Okay, let's say this position has radius of r variable from origin, so r radius. So if you look at closely to this third Amperian loop, the I enclosed actually guys cover the whole total current, right? Again, I repeat, for the biggest Amperian loop in the third region here, this loop cover the whole value of current. It means that the I enclosed for this case, right? It means that I enclosed for this case actually is equal to I, total current that enclosed within the whole Amperian loop. Okay, so again, you can simply find the H any point 2 pi r again, now I, so the H, you can find the I over 2 pi r again in phi directions, ampere per meter. Alright, so you can see from here guys, the R actually is a variable that will make difference within the H value. If the R become much larger than the origins, so you can see that the H will make decrease, right? Actually the H and R actually inversely proportional. So alright guys, so that's the idea how we solve this structure. So I would like to remind you that be careful with the limit. Alright, so you can see that this case involves volume current density, and the approach to find the I enclosed a bit different with the previous one. So for the case of volume, we just multiply between, or just do or perform dot product between J vector dot ds vector. So that's how we find the I enclosed for the case of volume current density. Okay guys, so I hope you can try yourself, and if you have any questions, so just let me know, and all the best.